ME204, Kinetic Energy of a Rigid Body. We've talked about the different possibilities of motion that we have. For translation, there's rectilinear and curvilinear. And when we're dealing with energy, the energy equation that we've developed works for this. However, sometimes we have motion that includes pure rotation, or rotation about a fixed axis, and general plane motion, where we have both translation and rotation. Well, certainly there's energy associated with rotation of a body, but how do we calculate that? What causes it? We've already talked about how work causes a change in kinetic energy, so there must be something with rotational work that causes rotational kinetic energy. Work is the product of an applied force for a known distance, and we've discussed this in relation to translating objects. If we have a constant force, then the work is equal to a force times a change in position. So what if we have a constant moment that's being applied? In this case, instead of a force, we have a moment, and instead of a change in position, we have a change in angle. So our work, for rotational work, is equal to a moment times a change in angle. We can represent a moment as a force times a moment arm, or a radius. We can write our work for a constant moment as a force times a radius, or a moment arm, times a change in angle. Notice that the equation for arc length is S equals r theta. So a force times the moment arm, radius, times a change in angle is equal to the same thing as a force times a distance. The only difference is that our distance in this case is an arc length instead of a linear distance. Also remember that theta in this equation is measured in radians. If we put degrees into this equation, then we'll get the wrong answer. What if we have a moment that's not constant, that changes? In this case, we would have to integrate. Here's a couple of examples. There's no rotational work done if there's no net moment. And there's no rotational work if there's no rotation. In this particular example, if I have a 1,000-pound rock that I'm pulling on with 10 pounds in a horizontal direction, then I would have a 10-pound frictional force resisting that motion and a normal force of 1,000 pounds at the bottom of the rock. If I sum the moments about the center of gravity in this case, then I have 10 pounds times a 10-inch moment arm plus another 10 pounds times its 10-inch moment arm minus the 1,000-pound normal force times the offset distance of 0.2 inches. Our moment in this case would be 0. How much work was done? Well, if the moment is 0, and if there's no net moment, there's no rotation, the change in angle is also 0, then our work is 0. Here's another example. Rotational work is negative if the moment is in the opposite direction of the rotation. In this case, I've got a bicycle wheel with a moment that's applied to the wheel of 60 pound-feet, but the rotation is in the opposite direction that the moment is being applied. In this case, the moment is taking energy away from the system and slowing the bicycle wheel down. So how much total work was done? Well, we've got a moment of 60 pound-feet times pi radians, that's the angle, but it's taking energy away from the system, so it's a negative work. So we have negative 188.5 pound-feet of work. For energy, there are two types of rotational energy in mechanical systems that we have to worry about. First is kinetic energy, or the energy of a rotating object. Second is potential energy, which is stored energy. For potential energy, we've talked about springs with respect to translating objects, but you can also have springs in rotating objects as well. If we have a cocked spiral spring, it has stored energy. However, we're not going to address that in this course, but I want you to know that it is a possibility. What about potential energy due to gravity? Gravity does not apply to rotation since gravity is in a single direction, so there is no rotational potential energy due to gravity. We know that the kinetic energy of a translating object is 1/2 the mass times the velocity squared. So what is our rotational kinetic energy equal to? If we replace our mass with a mass moment of inertia, and we replace our velocity with an angular velocity, then we get a kinetic energy equal to 1/2 the mass moment of inertia times the angular velocity squared. This is our rotational kinetic energy. Where does this come from? We saw before with translational objects that if we use the equation of motion F equals ma and ADS equals VdV, we could solve the equation for kinetic energy for translating objects. Well, we can do the same thing with rotation. We know from the equation of motion that a moment is equal to the mass moment of inertia times the angular acceleration. We also know that alpha d theta is equal to omega d omega. If we solve this for angular acceleration and then substitute it back into our equation, rearranging this equation and then taking the integral of both sides, we get that the integral of moment d theta is equal to the integral of our mass moment of inertia times angular velocity d omega. Solving this gives us 1/2 I omega squared minus 1/2 I omega squared. This first part of the equation is work. On the other side, this is our final rotational kinetic energy, and this is our initial rotational kinetic energy. So work equals kinetic energy final minus kinetic energy initial. Or in the case of rotation, rotational work causes changes in rotational kinetic energy. So we've seen these different parts associated with energy of a particle, and for a rigid body, the same things apply when we're talking about translation, where we have 1/2 mass times velocity squared for kinetic energy, mass times gravity times the height for potential energy due to gravity, or for springs we have 1/2 spring constant times the change in length of the spring squared. We can now add to this 1/2 our mass moment of inertia times the angular velocity squared to include rotational kinetic energy. If we have a 1 kilogram ball that's rotating at 2 radians per second with a radius of gyration equal to 0.17 meters, we can calculate the kinetic energy of this object by simply plugging in what we know. Our mass moment of inertia is equal to 1 kilogram times the radius of gyration squared, 0.17 meters squared. Our angular velocity is 2 radians per second. And so, if we put that into our equation, we have 1/2 times 1 kilogram times 0.17 meters squared times 2 radians per second squared. Carrying the units through, this gives us 0.058 kilograms meters squared per second squared, which is equal to 0.058 Newton meters, which is also equal to 0.058 joules. Our next topic is rigid body kinetics using conservation of energy.